Hi, it's Moser here with a quick tutorial on oxidation numbers. First we'll establish what they are, and by the end of this short video you should be able to assign oxidation numbers to elements in a compound. Let's go. So oxidation numbers, I've always felt, are a little bit strange. They're a way to indicate the distribution of electrons among the atoms in a molecular compound or in a polyatomic ion. Basically, they're kind of like charge, except we're dealing with atoms that haven't given up or gained an electron. So they're not like ionic charges in that really no exchange of electrons has taken place. So they're kind of made up, but they are useful. They're useful in doing some structural prediction if you get into further chemistry. They are used in some forms of writing and sometimes in balancing equations. If you go on in chemistry and you do oxidation reduction reactions, which are beyond the scope of a high school Chem 1, oxidation numbers come in handy. So it's a good thing to have seen. That said, we'll get you a little bit of practice, and that's about where we'll stop. Okay. The nice thing about oxidation numbers, if you are a rule follower, is they are rule-based. So that looks like a lot of rules, doesn't it? Here's something that you should be aware of. If you look at the ion reference sheet that you've been given if you are in my chemistry class, you'll notice that at the bottom, just below the common acids, you have a very abbreviated version of the rules for assigning oxidation numbers. Obviously, you'll have this reference sheet to use on quizzes, tests, and homework, so you don't have to memorize them, but you do have to know how to use them. Okay, let's run through the rules real quick. Atoms in a pure element have an oxidation number of 0. Well, of course, they're not sharing their electrons. So if there's no sharing going on, there are no oxidation numbers. If we look at a compound and we can figure out which element would have higher electronegativity. So remember, in general, that's moving towards the halogens on the periodic table and moving towards the top of each group. The more electronegative element in a binary molecular compound gets an oxidation number equal to the charge it would have had as an anion. Remember, the electronegative elements are going to be more likely, if they were bonding ionically, to form anions. So whatever charge it would have had, we assign that as its oxidation number to start with. The less electronegative element gets the oxidation number equal to the charge it would have had as a cation. Okay, that's fairly simple. You should, by this point, be able to pretty quickly determine what charge something would have. Now, fluorine has a rule all to itself. Fluorine always has an oxidation number of -1. Always, which is convenient because that's also the charge it always has. So anytime you see fluorine, you can immediately plop an oxidation number of -1 on it. Oxygen, well, oxygen has an oxidation number of -2 most of the time. There are a few exceptions, but we won't deal with them at this level of chemistry. So you can pretty safely assume that if you're looking at a compound containing oxygen, you can assign oxygen the oxidation number -2. Hydrogen has always got a +1 when it's with something more electronegative, and it can have an oxidation number of -1 when it's with a metal. These are really important. The algebraic sum of oxidation numbers is equal to the charge of the compound. Oh, which means in a neutral compound, the algebraic sum of the oxidation numbers has to equal 0. That's a fancy way of saying if you have a +2 oxidation number, you have to have a -2. They have to balance one another out, just like charge. Now, if you have a polyatomic ion, of course, it does have a charge, and the algebraic sum of the oxidation number has to equal the charge on the ion. These rules are for covalently bonded atoms. We don't typically call the electron arrangement in ionic compounds oxidation numbers, though you will see references occasionally to people talking about the oxidation state of an atom in an ionic compound when they mean its charge. Okay, let's do some practice. You will need your sheet with the rules, and I've actually copied both of these examples to the next page, so we'll go to a blank slate and we'll do these plus a few more. We'll start with UF6, which, if you know that U is uranium and you're familiar with naming molecular compounds, you'll know is uranium hexafluoride. I've developed a sort of little pattern that I tend to use when I'm doing oxidation numbers. I'll write the I'll write the compound there, and then over top of the first element in the compound, I will write the first thing that I can get a hold on, that I can assign an oxidation number to. I'm looking for something that's got a rule associated with it. And fortunately I have fluorine. Based on rule 3, fluorine always has a -1 oxidation number. Now, the thing is, I don't just have one fluorine. So what's the total negative oxidation state on all the fluorine atoms in this compound? Well, -1 times 6, because there are 6 fluorine atoms, fluorine atoms. So I have a total negative oxidation state of -6. Now, to make that equal 0, something plus -6 equals 0, doesn't take a rocket scientist to know that that's +6. Alright, now here's where I think this is really useful. We have to distribute that +6 among all of the uranium atoms. So we're going to put in here, we're sort of working down and then back up. I'm going to divide it by the number of uranium atoms I have. That's 1. So that uranium atom has an oxidation number of +6. And I tend to write the oxidation numbers directly over the atomic symbol for the element, not off to the side, because then it could be confused with a charge. And remember, these are not charged ions, so we're just writing their oxidation number. Okay, let's do another binary compound first, and then we'll move on to the trickier ones. Let's do this one, CH4, carbon tetrahydride. So, I'm going to write my compound. Is there anything in here that has a rule associated with it? Well, hydrogen has an oxidation number of +1 with more electronegative elements and -1 with metals. Is carbon a metal? Nope, sure isn't. So, hydrogen is going to have an oxidation number of +1. I'm going to write that underneath the hydrogen, +1 times 4. So I have a total oxidation on hydrogen of +4. Something plus a +4 must equal 0. That would be a -4 divided by 1. That carbon has an oxidation state of -4. Okay, let's do, well, I'll tell you what. Let's go ahead and do another neutral one, but one that's a little bit trickier. H2SO4 is sulfuric acid. And to start with, we want to, remember we have 3 things here, so I'm going to kind of make 3 columns underneath here. We want to look for anything that has a rule associated with it, and the first thing that I see is oxygen. Oxygen in general is going to be a -2, so we have -2 times 4. Oxygen lends a total oxidation state of -8. Now I have 3 things here that when added together have to equal 0. Oh boy. So, in this case, I need to find 2 pieces of the puzzle, obviously, and then I can solve for the third one. So, is there a rule associated with any other compound, or any other element in this compound? Why, yes, there is. Hydrogen. So, hydrogen typically has an oxidation number of +1 when it's paired with anything other than a metal, and neither sulfur nor oxygen are metals. So, I have a +1 oxidation state on hydrogen times 2 gives us a +2 here. Now, I could go ahead and really truly solve algebraically, but I think you can probably see that sulfur has to have a +6 oxidation state in total. So let's divide that by the number of sulfurs we have, which is 1. So that sulfur atom has a +6. Now here's something to be really careful about. When we're asking for the oxidation number on hydrogen, it is +1 because that's the oxidation number on each hydrogen atom. That's a mistake you don't want to make. The sulfur has the +6 because there's only one, and the oxygen has the -2. So these themselves do not equal 0, and that's okay. These equal 0 when we account for the oxidation number on each atom. All right, let's go ahead. I think you're ready. Let's do something with a charge. We'll start off with our old friend, the ammonium ion, NH4 1+. So remember that the algebraic sum of the oxidation numbers always has to be equal to the charge on the compound. Up to now we've done neutral compounds, so the charge on the compound is 0, but now we have a +1 charge overall. Easy enough to account for. So do we have anything in this compound, or polyatomic ion in this case, that has a rule associated with it? Yep. Okay, nitrogen has a +1 when it's not bound to a metal. Times 4, we get a total oxidation state of +4. We know that this has to equal +1. So something plus +4 equals +1. That would be -3. And if we divide that by the one nitrogen atom that we have an oxidation number of -3 for the nitrogen, +1 for the hydrogen. It algebraically equals the sum. The algebraic sum of the oxidation numbers is the charge. And very often you will see -3 is also the ion that nitrogen tends to make. It doesn't always work out that way, but it works out that way enough that, you know, when you see that, you think, yeah, I probably got that right. Okay, let's do one more, and then you'll practice on your own before you take your FIP quiz. Again, we have a charged substance. We have the nitrate ion. You're starting to master that. And there's a rule about oxygen, so we'll go to that. Oxygen typically has a -2 charge, and times 3 gives us a total oxidation state of -6. Okay, now -6 plus something has to equal -1. So that would be +5, and we're going to divide that by the 1, which really, yes, is sort of a formality. And we find that nitrogen here has an oxidation number of +5. It's not the 3 that we're used to, but it happens sometimes. It's okay. And that is, in fact, the correct answer. All right, you've got practice to do, and when you feel confident and you've checked yourself, you got a FIP quiz. Practice.